So in the last class we discussed about dynamics equations, which gives the relationship between stress and strain in a three-dimensional stress system. In this class we will discuss a problem on stress-strain relationship using dynamics equations only. The problem is given like this. The state of strain at a point is given by epsilon x 0.001, epsilon y minus 0.003, epsilon z 0, gamma xy 0, gamma yz 0.001, gamma zx minus 0.004. Now, he has given the 6 strain components acting at that point. He has asked determine the stress tensor. So we have to find out the stress tensor at that point. That means strains are given. We have to find out the stresses, and the elastic constant Young's modulus is given as 210 GPa. GPa, 1 GPa is 10 power 3 MPa, Newton per meter square. So you can write this as 210 to 10 power 3 MPa, and Poisson's ratio of the material is given as 0.28. Now, the procedure is very simple, so you have to use the dynamics equations now. You know that strains, they don't have any units, just their numbers. It is given like this. So stresses will be in MPa only. So whatever units of E is there, E and G units are there, in the same units you are going to get the stress values. So here I have converted GPa to MPa, therefore all your stress values will be in Newton per meter square or MPa. Now the procedure is like this. First we will find out the volumetric strain epsilon V, which is given by epsilon x plus epsilon y plus epsilon z. Here also the positive values represent tensile strains, negative values represent compression strain. That means there is increase in length in x direction, decrease in length in y direction, and there is no neither increase nor decrease in z direction. So that is the meaning of these values. Now epsilon V is the sum of epsilon x plus epsilon y and epsilon z. If you add all the three, you are going to get minus 0.002, because epsilon x is 0.001, epsilon y is minus 0.003, epsilon z is 0, you get minus 0.002 as the value of volumetric strain. Now, since E and mu are known, in dynamics equation we need to find G and lambda. G is the rigidity modulus and lambda is the dynamics constant. So let us find out those two. G is given by E divided by 2 into 1 plus mu. So this expression you should remember. So substitute the values and simplify. You will get G as rigidity modulus as 82.03 into 10 power 3 MPa. And dynamics constant also you should remember the expression. Lambda is equal to E into mu divided by 1 plus mu into 1 minus 2 mu. Once again you substitute the values E, mu, then simplify, you will get lambda as 104.42 into 10 power 3 MPa. Now, let us find out the normal stresses using the dynamics equations. There are 3 dynamics equations, one for sigma x, another for sigma y, and one more for sigma z. So sigma x, as you know, it is given by lambda into epsilon v plus 2g into epsilon x. Now you know all the values in RHS, just substitute and simplify. Lambda is this 104.42 to 10 power 3 into epsilon v is minus 0.002 plus 2 times d is 82.03 to 10 power 3 into epsilon x is 0.001. So you need to remember these equations, dynamics equations. So if they ask the derivation, you have to do whatever I have explained in the last class. If they give a problem, you have to proceed like this. And once you simplify, you are getting minus 44.78 MPa. So whatever units of E are there, same units you are going to get the sigma values. Negative sign indicates that it is compressive stress. So one thing you can observe here, even though the strain in x direction is positive, stress in x direction it has come as negative. This is because of the net effect of all the stresses acting in all the 3 directions. That is very important. It is not uniaxial stress. So stresses are acting in all the 3 directions. That is why, so you have got sigma x as negative here. Second, you are going to get sigma y using the same equation, but but instead of epsilon x, you have to take epsilon y. The first term remains same, 2g remains same. Once again, if you substitute all the values and simplify, you are getting there also negative value minus 701 MPa, which is once again compressive. So in y direction also, the element is subjected to compressive stress. Now third one, sigma z. Once again here, instead of epsilon x, you have to take epsilon z. The other terms remain the same. Substitute the values and simplify. You are getting minus 208.84. That is also compressive. So you can observe here that, so in all the three directions, compressive stresses are developing on the element for the given strain system, of course. Now these are the normal stress values, three normal stress values, sigma x, sigma y, sigma z. Now we have to find out the shear stress values also, because to find the stress tensor, we need to have all the six stress components. So shear stresses, as usual, they are given by these three simple equations. Tau xy is g into gamma xy. So gamma xy is given here, it is 0, therefore tau xy becomes 0. And tau yz is g into gamma yz. Gamma yz is 0.001. So g value you have got here 82.0 to 10 power 3. Substitute and simplify, you are getting 82.03 MPa. And tau zx, g into gamma zx. Gamma zx is minus 0.154. So if you substitute, you are getting minus 328.12 MPa. Now you have got all the six stress components. Three normal stress components, sigma x, sigma y, sigma z, and three shear stress components, tau xy, tau yz, tau zx. And if you want to write the stress tensor you lost, whatever you lost, this is the stress tensor, as you know. So write down the stress tensor sigma at that point. So just put the respective values there. So sigma x is minus 44.78. See here, tau xy is 0, tau xz is minus 328.12, and it is symmetric. So you can directly write whatever first two column elements are there, same elements will come in the first column. Now second row, so minus 701 is the value of sigma y. Then tau yz is 82.06, that will come here. So second row, second column remains same. This becomes 82.03, and lastly sigma z, which is minus 208.84 MPa. So this is the stress tensor at that particular point. So given the strain tensor at a point and the elastic constants, how to find the stress tensor at that particular point? So that problem can be done by using the Lami's equations, that is stress strain relationship for a three-dimensional stress system.